I'd like to present um, the project that's coming up, for CPSC 410. Specifically, I want to go over um, where you can find help on the course website, and then I want to go over exactly what the project involves. It is essentially a producer and consumer problem. So if you look on the course website on, well, weeks 12 and 13, you'll see this project here, simple producer consumer problem, producer signals consumer. If you open this project up, it will look like this. So I am going to, let's close unrelated projects and go to this guy. The way a producer consumer works is a producer is going to produce a certain amount of widgets and a consumer is going to consume those widgets. The problem is usually formulated in this way. So you're going to start some threads, and it can be any number of threads. And I'm going to start this producer thread. It's going to produce 1,000 widgets. Now, the way my producer, and I start a thread that's a producer, this is how many it's going to produce. And so I've got this for loop that is going to go through num count, and it will produce this many widgets. So producing a widget means I'm just incrementing this global count here. Now, for condition variables in this sort of problem, what's the intent is the producer produces something and then tells the consumer that it's produced something. It's these same few lines of codes that I've showed you. My producer is going to acquire a lock, and I've got this global that I'm going to use to protect all of my mutex here, that I'm going to protect all of my globals. I'm going to increment my global, which indicates that I produced one. And then I'm going to release this lock and call notify all. That will wake up every single thread that's waiting to be notified when the producer has produced one. The consumer is the thread that's waiting for the producer to produce one. The consumer is going to start off, and initially, you notice that I have this while loop that runs forever. There's only one place where I'll break out of that while loop, and that is if G count's equal to 0, which means everything has been, and G count's tracking the number of widgets to consume, and B done's equal to true. B done means that the producer is finished. That is what B done is all about. You start off with B done is false. The producer is what sets B done equal to true. So my consumer will continue to consume until this condition evaluates to true, and then I'm going to break. Now, the way the consumer consumes is, notice that I have the while true. I don't have any sort, I'm not accessing any sort of global here. I'm just looking at this while loop that goes on forever. So I will acquire a unique lock. I'm going to check this condition and this Boolean expression. If G count's equal to 0 and B done's equal to false, that means there's no work for the consumer to do because there are no globals, but the producer is not finished producing. So there's nothing to do, but the producer's not finished. So I'm going to put my consumer asleep. My consumer will go to sleep here, and it will release this lock. Now notice this is a unique lock. A unique lock is a lock that I can manually unlock. cv.wait will manually unlock this lock and put this thread to sleep. And this thread will stay asleep until the producer produces one here and calls notify all. When I call notify all, that will wake up as many threads as there are that are sleeping right here. And one at a time, they will acquire this lock and check this condition. If the producer has produced one, then G count is greater than 0. Or maybe B done's equal to false. If this condition is no longer true, then I'm going to, while owning this lock, I'm going to go to this next statement at line 48. And I'm going to check, why did this consumer wake up? Is it because G count is greater than 0? Is there work to be done? If so, decrement G count. Now, remember, if I'm here, if at this point, from this point on, from line 15 on, I own this lock. I release this lock on this lock or this mutex as soon as I hit cv.wait. But if I wake up again, I reacquire the lock. When I move forward in this code, I still own this lock. I reacquire it when I wake up. All right, so I've got this mutex. If something was produced, well, I'm going to consume it, and that's what this is. That's what this is simulating: consuming something. And I've got this report statement, which is not really interesting. It's just a thread safe cout statement. And then while running the lock, I'm going to check, hey, is it time for the consumer to bail? Is there nothing else to consume? And the producer is finished. If the producer is finished and there's nothing else to consume, I can break out of this loop, and then I can exit my consumer. Notice what's going on in my producer. It is going to produce however many widgets I tell it to. And I'm going to start off with 1,000 here, produce 1,000 widgets, and it will just count down and produce 1,000 widgets, incrementing this G count. And meanwhile, my consumer is going to be waiting for G counts, for any notifications from my producer. When it wakes up, if G count's greater than 0, I mean, it's either, if G count is greater than 0 before it even hits the CV.wait, it's never going to hit the CV.wait. It's going to get down here and it's going to decrement G count. And then it's going to check, is it time to leave? No. Then it comes back up here. Then it releases the lock. It releases this lock here, comes back up here, reacquires the lock, checks the condition. And as long as G count's greater than 0 and B done is equal to false, it's going to keep going. It's going to keep consuming. And this will work for, and this is how a producer and a consumer operates. And this is exactly what the project is that you're supposed to work on. So if you go to your project, I'm going to go to it now. Here's your project. Project 4, donuts, multiple waiters, student. It is a producer-consumer problem. So you're going to model a donut order fulfillment system. Multiple waiters are going to take orders for donuts. So the waiters are the producers. They're going to ask this file.io class, hey, do you have any orders? And the file.io class is going to provide orders to the waiters. And the waiters are going to set up an order and post it on this order end queue. That's producing something. And then my bakers are the consumers. They're going to be sleeping, waiting for orders to show up. And they're not going to do anything until orders show up, and as long as my waiters aren't finished. So I've got this file.io object. It's a thread-safe class that opens a file, parses and reads all the orders into an internal data structure, and then provides orders by this getNext method to waiter. So my waiter is just going to be pulling orders. It doesn't matter how many waiters I have. They're all going to be pulling orders from this thread-safe file.io object using this getNext method. An order looks like this. This is order 1 that has 10 donuts, order 2 that has 5 donuts, order 3 that has 12 donuts. And the waiter's only purpose is to get these orders from this file.io object, create an order object, and post it to the order end queue. Now I'm giving you some mutexes to protect all of these global resources. This is a global resource, and that's a global resource. You need to protect this global resource using this mutex order end queue. That's how you're going to protect that. And when you're protecting this order out vector, you're going to use the mutex order out queue. That's another mutex. So you've got multiple mutexes that you're using, one to protect this data structure and one to protect that data structure. The baker, the whole purpose of the waiter is to pull orders from this file.io object. Because as soon as it gets an order, it's going to create an order struct and adds that struct to the order end queue. And it's got to do it in a thread safe way using this mutex order end queue. When this file.io object has no more orders, when my waiter has pulled all the orders from the file.io object, then the waiter is going to exit and it's going to decrement the number of working waiters. That's a global. And so there's a global that keeps track of the number of working waiters. And so I can have 10 waiters pulling simultaneously from this file.io object. It's thread safe. It's not a problem. And so when you create a waiter, it's going to increment the number of working waiters. So if I create 1 waiters, the number of working waiters is going to be equal to 1. If I create another waiter thread, it's going to be 2, and on and on and on. But as soon as I run out of orders, the waiters start to exit and they start to decrement number of working waiters. When this waiter exits, number of working waiters goes down to, if it's at 3, it goes to 2. And then it goes to 1, and then it goes to 0. When it goes to 0, that means there are no more waiters. That means that all of the orders have been pulled from this file.io object, and they've been processed. The waiters are finished. It's time for them to go home. They want to tell the bakers that they can go home as soon as they processed all the orders. And the way they do that is by setting all work done is equal to true. But you only do that when all the working waiters are complete. That's going to notify the bakers that there are no more orders coming. And so at that point, all the baker has to do is pull all the remaining orders off this order in queue, process them by calling bake in box and order and putting them in this order out vector. So the baker, the waiter is the producer, the baker is the consumer. All the baker is going to do is sleep while there are no orders and all work done is false. It sounds very much like the producer-consumer problem I just showed you. It's going to be awakened when notified by the waiter. The waiter's going to awaken bakers whenever it produces an order and puts it in the order in queue. And so when the baker wakes up, if there's an order available in here, it's going to pull it out, pull that order off, and then it's going to call bake in box and order to take that order, order number 1 that has 10 donuts, and it's going to create a box to hold that number of donuts. Now, if the order has like, each box holds a dozen donuts, I think. So if the order has 25 donuts in it, it's going to require 3 boxes. 2 of them will have 12, 2 boxes will have 12 donuts each, and 1 will have 1 donut. So that's what bake in box does. It's a little bit of math, but it's not complicated. You just have to figure out how to cram all of these donuts into the minimum number of boxes to cram all these donuts into. Once you bake in boxed the order, you chuck it onto the order out vector. And when waiters, so when all the waiters are done, when all the work done is equal to true, and when there's no more orders in this ordering queue, then all your bakers can exit. So here's an example. Suppose there's a waiter and it's pulling in order 1 that has 10 donuts in it, like this first row here. Here's what will happen. This waiter is going to pull this order in from this MIO object. It's going to create an order object with an order.boxes is equal to 0 because it hasn't created the order yet. Then it's going to set the order number equal to 1 because it's order number 1 and set the order.number of donuts that you want to 10. And that's the order. It's an order up. It's going to safely put that order onto this order in queue using this order in queue mutex. And then it's going to signal all the bakers through the condition variable. One of the bakers is going to wake up, or all of them if you're using notify all, and they're going to check the condition. Hey, is the order in queue empty? Or if the order in queue is empty, if it's not, that baker is going to take that order off the order in queue, and it's going to call bake in box and order to generate 1 box of donuts, one box with 10 donuts in it. And it adds that to the order object. So the box goes with the order, and then that goes on the order out vector. So the waiter takes the orders, puts it in the order in queue. The baker will get the order and fulfill the order and puts it on this order out vector. And that's the way this is going to work. You have to synchronize this process and you have to do it correctly. Do exactly what I showed you in class. Don't use an if when you're supposed to use a while. Make sure and don't acquire and hold a lock for the entirety of a process's lifespan. For instance, for the waiter, don't acquire a lock and hold that lock until all the orders are processed. Then one waiter will do all the work and none of the other waiters will do nothing. So you want to make sure you follow what I showed you here. For a producer, you have this play going on where you acquire a lock, produce something, then you release the lock and notify all, and then acquire the lock again. You want to do this over and over again. So this way, if I have multiple producers, then each producer gets a chance at actually doing some work. All right, let's go back to here. So everything in file IO is given to you. You can check it out. And all it's going to do, the part of file IO that is going to be of most interest for you is get next, I believe. So let me open this up. We'll go look it at it. And it's under waiter, and there's file IO, and here's file IO. So all this stuff is private. Here's the public stuff. There's my constructor. There's the file that I want to order from. That's the file that I want to open and read orders from. And by the way, here's what a file will look like. This is a file that has no orders. This is a file that has 1 order. And this is a file that has a lot of orders in it. And let's go back to fileio.h. So this reset file name, what this will do is it's going to reload my file IO object. I pass in a new string, and reset file name will, where's reset file name? Here. It's going to load my data. And what load data does here is, well, load data is responsible for reading the file name, reading everything out of the file, parsing all those orders, and then filling up an internal data structure with all the orders that the file IO is going to track. Where's the internal data structure? Well, it's right here. This vector full of order objects. What's an order? Well, go and look at it. Well, here's this order. It's a struct that has, there's a number, there's the order number, there's the number of donuts. When I first pull it from the file, I'm going to have an order number and the number of donuts. The order won't be full yet though. So this vector will have nothing in it. So this vector full of orders is going to be populated automatically by load data. And essentially, when you first construct this object, you're going to construct this object and pass in a file to order, a file to load from. That file to load from will load all the data, and you can see it here. So let's see, file IO, there's the file name. I call reset file name. Reset file name will load all the data, and boom, that's it. My file IO object will populate this vector full of all the orders. Now, once again, the boxes in each order will not have anything in it. That's going to be done by the baker later on. And once I've done that, I've got this file IO object that has this thread safe get next method. Now, the whole thing is thread safe. So multiple waiters can pull from this file IO object. And this get next object, this get next function is how you get the next order in line. So if I pull, if this my orders vector has order 1, 2, 3, 4, 5, get next is going to get my first order, then my second, then my third, then my fourth, then my fifth. And it doesn't matter how many waiters are actually pulling from get next. It's a thread safe implementation. And you can see the thread safe part of it down here. Require a lock. It's got an internal lock here to make sure that it doesn't matter how many waiters are trying to pull from this object. Only one of them will get past this on this lock at a time. I'm going to check, are there any other orders? If there are no more orders, return, hey, there's no more orders, you're done. Otherwise, grab that order and erase it from my orders vector that's internal to this file object. And then return it. Return that order object here so that my waiter can process it. All right, so the things that you need to implement are waiter.cpp and baker.cpp here. So they're not overly complex. If you look at waiter, here's waiter.h. Here's the private, there's the ID of the waiter that I want to work with, and here's the public part. And there's an explanation of what each everything should do. Here's my constructor. So whenever you create a waiter here, you need to increment the number of working waiters to indicate that a waiter is started. So this number of working waiters is a global. So where is it? I don't see it here, and I don't see it here. So if you look in this file, xturns.h, you'll see, where is it? Mutex, atomic, number of working waiters right there. That's where it is. It's declared in this file. It's not really declared. It says there's somewhere in this project, there is a variable called number of working waiters. What xturn means is it's a note to the linker, and it says, it's a note to the compiler. It says, at linking time, find where number of working waiters are. If you have 10 files that you want to link together, xturn says that in one of those files is going to have a number of working waiters defined. So this allows you to declare a variable in one place and share it amongst other files. So when you create your waiter here, you want to increment that global variable. Where's it defined? I think it's defined here. Look inside a 410 project. There it is. There's the actual definition. So when I compile all of these together, my baker and my 410 project 4, my file IO, my waiter, and my all of these CPP files, when I create all these object files, when I link them together, this is where number of working waiters is actually sitting. But my waiter, waiter is waiter.cpp doesn't know that at compile time. It just knows that there's an extern here, and the extern says that somewhere at link time you will find a standard atomic int called number of working waiters. It's defined right there. All right, so you go back to waiter. Make sure when you create your waiter, you increment number of working waiters. Okay, number of working waiters, so it's an atomic, don't need to protect it. It is global, you don't need to protect it. You're also going to want to set all work done is equal to false to indicate that there is work to do when you first start. So all work done is also a global, it's also externed, and it's also defined in 410 project 4.cpp. I have get next. Get next is going to get the next order. And what get next is going to do is it's going to call the global file IO object. So the global file IO object is, let's see if I can find that. Mission variable right here. There's my global file IO object. It is also defined here, right there. That's where it is. So get next is actually just going to pull from that file IO objects the next order that it's going to process. And that's as illustrated in this process here. Waiter pulls from MIO the next order to work on. So go back to here. All right. So remember, file IO has its own internal locking, so it's thread safe. It doesn't matter. So this is going to return, what get next is going to do is it's going to call in the file IO object, try to get the next order. Get next from the file IO object, it's going to return either success, wait a minute, that's not, get next, either success or no orders. Either it gets another order or I'm out of orders. And that's what I'm going to get from the waiters get next. So it's going to return, it calls into file IO to get the next object. And whatever file IO returns, if it returns success, then what's in an order is another order. If it returns no more, if it returns, what was it going to return? Where's file IO? Here. If it returns no orders, that means we're out of orders. All right, back to waiter. So that's all get next does. You have to implement that. So that's just going to call in that global object. This is going to be the hard one, be a waiter. So this is going to run the loop. This is the loop part of the producer. So it's going to call get next over and over again. And as long as it can get an order from this global file IO object, it'll get one order at a time. It's going to put them in the order in queue, make sure minding that you use proper synchronization so that multiple waiters don't try to hit that order in queue simultaneously. It's not a thread safe API. You have to make it thread safe using the order in mutex order in queue that I provided you. Once it gets an order, it'll put it there, and then it's going to signal the bakers using the CV order in queue condition variable. So with a notify all. All right, once it does that, that's going to presumably wake up some of the bakers, and the bakers are going to consume those orders. When my waiter is finished, that means when get next starts to returns, what was it again that it returned? No orders. When get next returns no orders, my waiter is done. So it can exit the loop where it keeps pulling from that MIO object. It'll decrement number of working waiters. And if the number of working waiters is equal to 0, it's going to set all work done is equal to true. And most importantly, it's going to signal the baker one last time before it exits, just to wake up the baker one last time. Say, hey, I'm done. You can leave whenever you finished all your work. So that's the waiter. The baker is here, and I'm going to close others because I'm getting too much open. And I have And there's my header file for my baker. So there's a rudimentary, I put some stuff in here. Notice I've also got externs, and I've got this baker.h file. The baker's also got an ID. So let's see, this is private, bacon box in order. This is what bacon box in order are supposed to do. Gets the number of donuts. So I'm going to bacon box in order. I pass in an order. So it's going to get the number of donuts out of there here, because the order will have a number of donuts. It's going to get those number of donuts, and it's going to package them up into a box. And a box is a class that will hold 12 donuts. So if my order has 16 donuts in it, that's going to be 2 boxes, one with 12 donuts, one with 4 donuts. So if my in order dot number of donuts is equal to 13, that's also 2 boxes, one with 12 donuts, one with 1. Then it's going to append those boxes to, those boxes are going to be appended to this guy here, boxes right there. So those 2 boxes will go right there. So now I have my order with my order number and my number of donuts, and the boxes are symbolizing the filled order. And that's all this does. When it returns it in order, when you call bacon box and you pass in an order, when it returns, this vector should have the equivalent number of boxes with the equivalent number of donuts in them. All right, baker, well, the ID just identifies baker. Now here's the meat of the bee baker. So this is the consumer part of it. This is the while true, then consume part. So you can look at this producer consumer. You want to look at, where's my consumer? This, for an example of, I'll give you an idea of what's supposed to happen. Something like a while true, and then you're going to consume. You're going to check this. There's your condition that you're waiting on, and then you're going to wait if nothing has occurred. And for the baker, you're running a similar loop. You're going to sleep as long as there are no orders to process, and all work done is false. That means none of the waiters have awakened. They haven't put an order on an ordering queue. There's really nothing to do. The bakers can't do anything until they get an order. So they're just going to go to sleep. They're going to be awakened whenever a waiter notifies them through notify all. When the waiter has gotten an order and placed it on an ordering queue, when it calls notify all, that's going to wake up the baker. So, and then the baker is going to check. So if there are orders in the ordering queue, then it's going to get that order and passes it to bacon box in order, so it can create a box with a number of donuts in it. And once it does that, it's going to take that order object that now has the box donuts, and it's going to chuck that onto here, the order out vector. And so that's essentially all my baker is going to do. It runs a loop and efficiently sleeps until as long as there are no orders. And as soon as an order shows up, or one of my waiters is done, it's going to awaken. It's going to see why it awoke. If it awoke because there's an order, it's going to process the order. If it awoke because there are no more orders and the waiters are and all done's true, then it's going to exit. So this is what you're going to be used to be notified in the baker. And all work done is going to handle the case of all work done is the bool that handles the case of whether the waiters are finished or not, because all work done starts off as false. When the waiters have processed all the orders, they'll set all work done as equal to true. So the baker is going to be watching this as well. And so this project, is a direct application of producer and consumer. You should find it pretty straightforward. File IO, it's all given to you. Baker, you've got to implement. Waiter, you've got to implement. Other stuff, other things to look at. Here's an explanation of what externs are. I've already given you that, but you can read it again if you want. And the only thing that what I'm going to grade is your baker.cpp and waiter.cpp. I'm going to make sure that you're using both the mutic mutex order in queue to protect the order in queue, and the mutex order out queue to protect the order out vector. I don't want you to use just one. I want you to use both. I want this to be as concurrent as possible. And when you run it, I'm just going to see what your average points are. And I think this thing runs even if you don't do anything. So if I build this, not that one, this one, build it, and you run it, it's going to run all these tests, and it's going to tell you whether you succeeded or failed. And it tells you how many donuts are made, how many it should have been made. And so it gives you some notion about whether you're off by one or not, or whether you're off by a lot. And if you get the multi-threaded portion of it wrong, you're going to fail all of these. These should all be precise. Now, I wonder if I have a correct run. I think this is a correct run output. If it runs correctly, it should look like this. Well, but of course, this depends on what I pass in this file here. So if I run this file, here's what your correct run output should be. You get 100. So you'll get a grade from this. And that's it. That's the project you're going to work on. This project simulates basically a donut shop where people are taking orders. When they get orders, they pop it up on the little turnstile thing, and the bakers, which is the order in queue, the bakers will then take those orders, bake those orders, and put it in an order out queue, and then it's ready to be served. It's a direct application of producer and consumer. So with that, I think that's enough for the next project that you're working on. If you have any questions, you can send them to me. This is a little bit harder, but if you understand the producer and consumer, this should be a cakewalk for